Good morning, ladies and gentlemen. Welcome to session We.B.4, Lasers and Sources. My name is Selina Farwell from Lamentum. I'll be presiding over this session. Please can I invite the first speaker, Takuro Fuji, to represent a 16-channel membrane directly modulated laser array on silicon for 2-kilometer transmission of 112 gigabits per second PAM4. Thank you.
Thank you for the introduction. My name is Takuro Fuji from Entity Device Technology Laboratories. Today I am here to talk to you about our recent progress of membrane directly modulated laser array on silicon. So, as many of you know, the number of internet-connected devices and internet traffic increases rapidly. And today, data center consumes 1 or 2% of global electricity. And our company already decided to deal with that. And the company aims at carbon neutrality of data center sectors until by 2030. And in this context, our research group are developing, trying to establish a new network within data centers. In order to develop network within data center short distance communication, there are several basic requirements. One is low power consumption, because we have to deal with power consumption in data centers. In this perspective, directly modulated lasers, or simply DML, with small active region is important. The second key is low assembly cost, because we need a tremendous number of devices for such short distance optical communication. And in this perspective, to use the photonic integrated circuit is important because we can use mature silicon process technologies that makes us possible to integrate several functional passive devices in a single chip. The third point is a small footprint because we have very limited space, so we need high shoreline bandwidth density. To meet these requirements, we're developing a membrane DML on silicon. The device consists of a membrane structured laser together with a spot size converter, so that the efficient optical coupling to the high-end fiber is achieved. The device itself has a very thin, let's say 350 nanometer thick 3-fiber membrane layer buried with a PN type indium phosphide layer and sandwiched between low refractive index silicon-based materials, so that we can achieve the high optical and carrier confinement. They both helps to reduce the power consumption. And since we have membrane structure, we can form the surface grating just above the active region, so that we can achieve single mode operation. And in addition, we can easily increase the coupling coefficient of the grating, so we can reduce cavity length. That also makes us possible to reduce the power consumption. And finally, since we fabricate the lasers on silicon, the process can be scalable. Let's say we can use a large silicon wafer to fabricate these lasers. And in the future, we can integrate several functional passive silicon photonics-based devices with this laser. And this is the general fabrication procedure. The fabrication begins with epitaxial growth on indium phosphide substrate. We glue indium gallium arsenide edge stop layer and MQW layer and bond this epitaxial wafer to the silicon wafer with an intermediate silicon dioxide layer. And then we remove the indium phosphide substrate to obtain this very thin 3-fiber layers on silicon structure. And we define MESA stripe and bury the MESA to fabricate buried heterostructure by carrying out the regrowth of indium phosphide on indium phosphide thin film bonded on the silicon. And then we form the P and N-type doping layer by zinc thermal diffusion and silicon ion implantation. And after that, we form the indium phosphide MESA, a tapered MESA, and we form the spot size converter by depositing the silica-based materials. Among them, the key point of our fabrication procedure is to carry out the epitaxial growth after the heterogeneous integration. So why we use such unique fabrication procedure? This is because it makes us possible to easily align this device to the silicon photonics devices in the future. And another important point is the capability of using mature silicon processes to fabricate this structure. However, the problem is high temperature MOVP procedure induces the thermal strain. So the key to how we can achieve the growth after the heterogeneous integration, and the key point is to use a very thin 3-5 layer, which is less than the critical thickness. On the left shows a schematic of the heterogeneous wafer and the CTE of the different materials. Since the CTE of silicon and indium phosphide is different, there is a thermal strain at high temperature. Let's say the bonding temperature is 200 degrees Celsius and the growth temperature is 600 degrees. The thermal strain is calculated to be 800 ppm. And the corresponding calculated critical thickness is 430 nanometers. This means that we should not observe any dislocations even after the high temperature process when the 3-5 layer is thinner than that. So that we can fabricate membrane structure layer even we carry out the epitaxial growth after the heterogeneous integration. And we have so far developed several devices like lasers, PDNs, modulators using that technologies. But today's talk is about a 16-channel DML array with narrow shoreline density. The device is designed for high bandwidth density, so there is a 16 output ports in 1.11 millimeter wide facet. And this layout is possible because we use the low-loss SiOX waveguide. And each DML has a 100 micron long active region. And that consists of two DFE sections, the tuning, and to obtain the asymmetric optical output from this side with single mode. To develop such, multi-channel lasers, of course, uniformity and yield is important. On the left shows a cross-section of our laser. The laser consists of indium phosphide membrane. The thickness is 340 nanometer, and the device is on silicon. And there is a contact layer and contact metal layer. And this time, we newly adapted the non-alloy electrode as a contact metal material. And previously, we used alloy metal. And on the right compares the IV characteristics of 16 DML arrays with alloy and non-alloy electrodes. And as you can see, non-alloy electrodes result in a smaller differential resistance with better uniformity. To measure the fabricated devices, we used RF probe one by one, and the optical light is coupled to the high-NF fiber with an index matching oil. As you can see, no scattering is observed during the waveguide. That means the low-loss SiOX waveguide is fabricated. And here is the static characteristics at room temperatures. On the left shows the LIV characteristics. Middle is the lasing spectra, and the EO response on the right. We achieved the threshold current of less than 1.3 milliamps, fiber coupled optical output power of greater than 1.0 milliwatt, and average differential resistance of 37.3 ohms are obtained. And we observed the single mode lasing with a very small wavelength variability, and the average F3dB is about 26 gigahertz. And we carried out the bit error rate measurement using 28 gigabaud PAM4 signal at room temperatures. On the left is back-to-back, and on the right is a 2-kilometer transmission for all 16 channels. And we achieved 2-kilometer transmission of 56 gigabit per second PAM4 with only 9 tap simple linear equalizer, and corresponding energy cost and bandwidth density is about 800 gigabps per millimeter with 0.65 picojoules per bit. And we actually carried out the same measurement even at 50 degrees Celsius, and we achieved the bit error rate below KP4 factor limit for all 16 channels after 2 kilometer transmission. And in addition, we have confirmed there is no electrical crosstalk. For this measurement, we use multi-channel RF probe. And as you can see, in this case, channel 2 and channel 6 are simultaneously driven. And we measure the bit error rate of channel 6 with and without driving next channels. And we compare the bit error rate of these three curves. And as you can see, the bit error rate curve is almost identical. This means that the electrical crosstalk is negligibly small. And finally, we further increased the bit rate to the 56 gigabaud, means that 112 gigabps at room temperature. To increase the baud rate, we need to increase the number of taps and adding the nonlinear equalizer. And we measured due to the time limitation, we measured the four channels with 4 different SIOX wavelength lengths. And we measured the bit error rate before and after the 2 kilometer transmission. And we confirmed that we can reach the bit error rate of below KP4 factor limit. And we've also confirmed all 16 channels I diagrams and bit error rate with an received output power of about 0 dBm. And all channels exhibited a bit error rate of below KP4 factor limit, and the I patterns are almost identical. The corresponding energy cost and bandwidth density reaches about 1.6 terabit per second per millimeter with an energy cost of 0.33 picojoules per bit. To summarize my talk, we have achieved the demonstration of 16-channel DMLs on silicon, and we've demonstrated the 2 kilometer transmission of up to 112 gigabit per second at room temperature, and actually 56 gigabps at 50 degrees Celsius. The corresponding short-range density and energy cost is about 1.6 terabps per millimeter with an energy cost of 0.33 picojoules per bit. And based on these results, we believe that our DML on silicon and its fabrication procedure as well are a promising way to manufacturing PICs for efficient light sources in future data centers. Thank you for your kind attention.
Thank you. Very good talk. Any questions? Okay, I'll ask a question. Could you say about the assembly and how you're driving the PIC with 16 channels?
How to drive 16 channels?
Yeah.
Okay.
What is the? Yeah.
Okay. Actually, our colleague tried to fabricate the flip chip driver that matches to the 16 channel. All right. So we can use that flip chip technology. We think that's a promising way.
So the measurements you did were all individually probed or wired, were they?
I'm sorry?
You had one driver for this paper?
In this paper, no, not yet. This is, we measured one by one.
Exactly.
We didn't integrate driver yet.
Yeah, thank you.
What's the reliability like? Have you done any testing?
Okay, good question. Yeah, reliability is one of the most important things, and now we are working with that. And let's say we don't have slide today, but we have tested about 2,000 hours at 80 degrees Celsius, and still emitting. But we need to improve.
Time for one more question.
So thank you very much for the nice talk. So actually you mentioned that you are now preparing the driver IC. Mm-hmm. So actually this energy per bit is only for the DML, or this membrane laser. Mm-hmm. Do you have any estimation regarding energy per bit with your driver?
Okay, thank you so much. Yeah, I'm not a professional, but our group, roughly estimates that the laser and driver has comparable energy consumption. So, let's say, now in this case, we achieved 0.33 or 0.6 picojoules per bit, and a similar power consumption. So the driver with laser is about between 1 to 2 picojoules per bit. And for temperature controlled condition, we also need tech. But if we reaches uncool, we can achieve the driver and laser with 2 or 3 picojoules per bit.
Thank you. We have to stop there. If everyone would like to thank the speaker, thank you very much.
Thank you.
Okay, our second speaker and talk is monolithic FMCW tunable laser with high modulation linearity and narrow line width. And the talk will be given by Limeng Zhang from Eindhoven University.
Okay, good morning, everyone. I'm excited to be here to share my research on the monolithic FMCW tunable laser with high modulation linearity and narrow line width. Okay, let's see what we can expect from our this talk. First, I will have a background introduction. Then I will dive into the device itself. It's about the tunable laser structure. And afterwards, I will walk you through the measurement setup and the related results we have been obtained. Finally, is conclusion. Okay, our story is starting from LiDAR. LiDAR is so popular recently as LiDAR could provide high accuracy and spatial resolution. It could detect the distance in a very precise way and create a 3D map of the environment around. So it's excellent to detect the fine details, which make it very ideal for some applications like self-driving and robotics. As a company, you development predict the LiDAR market will keep going from 2020 to 2026 and also in the future couple of years. So the huge growing market also motivate more research into the LiDAR. There are mainly two technologies employed for the LiDAR theory. One is based on time of flight. The other one is based on frequency modulated continuous wave. In FMCW LiDAR system, a linear modulated triangle frequency signal with triangle shape is emitted from the emitter. From the emitter, it will arrive at a target, and the return signal from target will mix with a reference, and be coherently detected by a balanced photo detector, and the beating frequency between the reference and the return signal can be determined. Finally, the distance and the velocity can be derived from the beating frequency from rising up and falling down edge. So that's the first advantage we can get from FMCW LiDAR. Additionally, because it's a coherent detection, so from the receiver view, the sensitivity can be dramatically improved. So it's good for long distance ranging. Also, according to the coherent detection, make it more immunity to the inference. Because it reduces the peak power of the laser source, and it could operate under the communication wavelengths, so it removes concerns to eye safety. So what's the shortage? Well, I would say that's a higher complexity from the view of chip design or from the view of the source design. However, if we consider about its function, let's say it can measure distance and velocity at the same time simultaneously, so it reduces complexity in the view of system level. And also, if we employ the wide tunable laser as a laser source, as a wavelength steering, you get the beam steering in one direction naturally. So that's also helpful to decrease the complexity from view of system. Okay, there are multiple indicators can be used to evaluate a laser source. But in this talk, we are going to talk about linearity from the view of FMCW. First, we construct a frequency modulated signal with a linear function, like this triangle you can see. And then we construct another signal. We introduce the recessional arrows for each point, and the root mean squared of the recessional arrows is common like 3 megahertz. And also introduce another 20 megahertz signal. And what we can see from the analyzed results, if it's an ideal signal, well, the FFT peak is quite clean, and the bandwidth is a resolution we can derive. And it quite depends on the frequency excursion we can generate from the triangle signal. But as the linearity increased, the peak moves a lot, and the bandwidth of the peak itself broadened. So both accuracy and resolution is getting worse. That is bad. Okay, currently there are multiple approaches to overcome these nonlinear issues. Let's say, pre-distortion is a very popular and simple way to correct the output frequency linearity. Actually, basically it relies on the interactive learning controller and update the voltage signal on the source. Normally, it's against source like DFB or VCSEL. So recorrect the signal on the laser itself can produce a very linear frequency modulated signal. It's simple, but the time drift, time delay in the system should be considered. The other way is to employ an external modulator, like a single sideband modulation, which is very good for linearity, but we have to consider other aspects like cost-expensive electronic components, and the frequency excursion based on this method is limited by the bandwidth of the modulator itself. Okay, in this topic, we are going to explore FMCW tunable laser structure. This is a schematic view of the laser cavity. What we can see here is a ring cavity and connected by a MMA coupler. A mirror reflector is connected to one of the waveguides from the coupler, which force a light propagate in the cavity in single direction. And the other waveguide is connected to the other output from the MMA coupler, which is output waveguide we have. Okay, to select a single mode, we have 3 cascaded asymmetric Marzana structure here. My pointer is not working. Okay. Along with the gain section, the phase shifter is modulated to generate FMCW signal, which is voltage driven and has very low power consumption. Finally, this structural laser is fabricated by Smart Photonics, who provide standard building blocks, and it has open access to public. So that is a real picture of our laser chip. As I mentioned, the phase shifter in the cavity is the crucial component we have in this design. So what's the relationship between the internal phase variation and the output frequency modulation? We start from the round-trip phase equations here. With mathematical transformation, we can derive the final equations as 4. So what we can say is, if we can apply a linear phase modulation in the cavity, naturally we can get a linear frequency modulation. There's a constant factor here. Subscript A means active, subscript P means passive. So I think we get what we want, and then it's about experiment. Okay, before that, we had to prepare something. The integrated chip is mounted on a PCB interposer here, and it electronically connects with wire bonding. Because we have this PCB, all the pins on chip are found out by the cables from PCB. And finally, the cables connected the different equipments like SMU, low noise, current source, etc. With this assembly, the whole PCB assembly is mounted on a cooler. So finally, the temperature control is achieved with water cooler. And with this experiment, the temperature is operation under 18 degrees. Okay, with this whole assembly, we make a fiber-based test setup. So the first phase of measurement is about laser performance, basic laser performance, including tuning range, SMSR, LLV, intrinsic line width. The second part is more important, that is linearity analysis, including the frequency excursion, recessional frequency errors, which mentions how nonlinear it is. Lower is better. The other factor is linearity correlation coefficient R squared, which represents how linear it is. Okay, with optical spectral analyzer, we measured optical spectrums for the whole tuning range. Finally, we get a tuning range from 1512 to 1563. It's 51 nanometer range, and SMSR is better than 40 dB. With the parameter in the test circuit, we get our L curve showed here, and we can derive the threshold is 42 milliampere at 1535 nanometer. And output power delivered by the laser chip can be estimated to be plus 2.4 dBm. Also, we can derive the series resistance from VI curve as around 3 ohm. By using We.B.4 solvent equipment, we measure the frequency noise spectrum like this, and we can derive the intrinsic line width is 16 kilohertz. That is quite low for our applications. The second part is about linearity analysis. AWG equipment is here. It's used to apply triangle modulated voltage signal to the phase inside our peak laser, and the output light is coupling through a lens fiber and through isolation and some optical fibers, which are not shown here. And finally, coming to a fiber-based interferometers. The delay line is 2 meters. The delay time is around 10 nanoseconds. With a balanced detection, the real-time waveform is captured by the oscilloscope here, which is showed in the following picture as a blue curves. So now we get the raw data about the real-time waveform. And by a Hilbert transform, we can easily calculate instantaneous frequency for both falling down and rising up edge, from where we can derive the frequency excursion is 1.8 gigahertz. And by the linear fitting, we can derive the recessional frequency as the right curves, and the RMS recessional frequency errors for both sides is 2.5 megahertz and 4.5 megahertz. The linearity correlated coefficient is as high as 99.993%. Also, with the raw data from the blue curves, we can derive the resolution by FFT calculation. By Merrill's bandwidth of this FFT peak, we can derive the detection resolution is around 17 centimeter, which is quite close to the ideal case in our design. Also, we explored the linearity under the tunable range with 5 discrete wavelengths here, which are shown here with the blue dots and the red dots. So the linearity correlation coefficient is better than 99.97, and the RMS recessional errors is better than 7.9 megahertz. And if we calculate the resolution in space, it's better than 25 centimeters. Okay, let's come to the conclusion. An integrated linear FMCW laser source is experimentally demonstrated with 51 nanometer tuning range, and down to 16 kilohertz intrinsic line width is observed. 1.8 gigahertz frequency excursion is achieved. Linearity correlation coefficient is better than 99.97%. And what we can say is any phosphide generic PIC technology is promising for C-band FMCW LiDAR. Also, we will conduct more performance research on this type of laser in the future. Okay, I would like to stop here. Any questions? Thanks for your attention. Thank you.
What power is required for the output of the laser in the system?
I'm sorry?
What output power is required for the laser in the system?
Okay, the output power is measured through a lens fiber. From the lens fiber, the power we measured is minus 7.66. But there are some couplers, on-chip couplers and off-chip couplers, and also we consider the coupling loss. So the power we can estimate it, which at the end of the laser is 2.4 dBm.
And is that enough for a system?
For the system, as high as possible, I would say. So we also have a target for the next round. We hope it could be 10 dBm. With this test, we use alpha as well. So currently, it's not an issue to demonstrate linearity. But in the future, high power will be there.
I think we have to end there. We're out of time. Thank you very much.
Thank you.
Okay, our next speaker is Alessandro Brognoni from University of Pavia. We'll be speaking about frequency locking on a DDO OFDM system with 2 optical carriers using a silicon nitride PIC.
Thanks. Good morning. I'm Alessandro Brognoni from the University of Pavia, and today I will talk about the work carried out with the University of Southampton and Huawei. As most of you know, integrated photonics nowadays is employed in many fields, going from quantum computing to mid-infrared generation. And today we'll focus on terrestrial communication. And the main target application of this circuit we developed are superchannel transmission and terrestrial beating note generation. And as I've seen these days at the ECOC conference, the trend for the photonic integrated circuit is to increase the number of components per PIC in order to increase the data rate of the optical communication. And going into this direction, what we want to have is a laser with multiple circuit with multiple laser sources, and we have to cover, we have to exploit all the bandwidth that we have available. And but this means that the integration of a high number of components leads to thermal crosstalk, and this thermal crosstalk can lead to a frequency drift of the laser that we have that is expected to be in the order of seconds or millisecond scale. And so this can lead to the overlap of neighboring channels, as we can see. And with Huawei, we decided to create a circuit that is able to lock multiple lines. And we also demonstrated two-channel DDO FDM transmission that was stabilizing frequency. So the idea is to create a photonic integrated circuit that is able to manage different laser sources and features an IQ ring resonator that we call locking ring resonator, whose transfer function is shown in figure in blue. And what we want to do is to place the laser emission in the inflection point of the transfer function. And once the laser drifts, we can detect the power variation at the output. And then we also design the FSR to satisfy the channel spacing between locked lasers, and we set it at 50 gigahertz so that we can create a dense WDM system. And then we use a silicon nitride on insulator platform that was fabricated by Ligentech, and as input sources, Huawei semiconductor models that we use to simulate the integrated ones, and I'll show you later how, with 10 kilohertz landwidth and tens of milliwatt output power. And these lasers were thermally tuned, and they are controlled in temperature by a thermoelectric cooler. So in order to provide a multi-channel operation, we have to integrate also silicon modulators at the input so that we were able to code each laser information, and so we can distinguish one laser from the other one. And the silicon nitride platform that we used provide low thermo-optic coefficient that is good for our looking resonator, since it is the reference of our circuit. And then we have low optical loss that leads to large Q factor for the ring resonator. And what we want to have in the end is a circuit like this, where we have multiple channels and that are managed by a DSP unit. And we want to tap part of the power and feed it to the silicon nitride peak. And this is the fabricated chip, where we have 16 inputs for a number, for 16 possible input lasers, 16 modulators, each one for each laser. Then we have the locking ring resonator that is shared among all the lasers, and 2 outputs. And in the end, the chip was fully packaged, aligning optical fiber array at the input, and placing on-chip photodetectors at the output. Also, a thermoelectric cooler was placed at the bottom of the chip. So this is how the algorithm for the stabilization works. We have a laser at the input at one input, tuned at frequency f1. The laser goes through the modulator that is coded if we have another other input sources, because we want to distinguish each laser from the other one. In this case, we have only one, so we don't need it. So we go through the locking ring resonator, and what we have is that we have to tune the laser around the inflection point of the transfer function. And we also split part of the power before entering the locking ring resonator, so that we track, taking the ratio between the outputs, we're able to neglect the fluctuation that may arise from the power changes in the laser. And we can consider only the fluctuation that comes from the frequency drift. And these are the static characterization of the 2 outputs. So we can use this information that are processed by a Python-based microprocessor, and we can send a signal back to the laser that is able to thermally tune the laser back to the initial position. And this is a setup that we developed at the University of Southampton, where we can see the electronics, the peak, and the lasers. So the setup can be extended also to more channels, and as a proof of concept, we decided to try with 2 channels. And in this case, we have to modulate each modulator at the input, and we decided to use CDMA encoding so that we were able to differentiate between different sources. And then we can place the 2 lasers at a distance that is multiple of the FSR, and in this case we decided to put them at a distance of 50 gigahertz, and then we use the information to stabilize the laser as we've seen before. And once we have the stabilized two-channel system, what we wanted to do with the University of Southampton was to develop a complex transmission. So we couple part of the power of each laser, and we use one output to generate a two-channel DDO FDM transmission with 50.244 gigabit per second per channel. And this is the situation. We have two channels separated by 50 gigahertz spacing. Then we have a guard band of 160 megahertz. And these are the subcarriers we generated with the discrete multitone technique, so that we were able also to detect small changes due to the granularity of the system. And then we considered the situation when the algorithm was working and where it was not working. So in this case, we don't have feedback connection. So to characterize the stabilization of the system, we need to take the other output, detect the 50 gigahertz tone generated by the separation between the two lasers. And then, since it's an high frequency content, we want to then convert the frequency with a wave generator, and we read it using an RF spectrum analyzer. In order to simulate the behavior of integrated laser, we externally perturbed one laser acting on the thermoelectric cooler. And what we end up with was this shift of the bit knot with the 500 megahertz amplitude and 50-second duration. And then what we have at the transmission side is an overlap of these two channels that is equal to 340 megahertz. And as a figure of merit to classify our system, we decide to consider the signal-to-noise ratio of the edge subcarriers, of the subcarriers that compose one channel. And you can see many lines that are the different acquisition, different time. And when we have a good transmission, we have 8 dB. When we have a bad one, the conditions are worsening, and we can reach 0 dB. And so, as we can see from the picture, we focus on the edge subcarriers, and we can see where there is the overlap. We have a worsening of these performances. Instead, if we activate the feedback signal, we can manage to correct the 50 gigahertz tone with an adapted algorithm. And then at the transmission side, what we obtain is an increase of the performance of our system, and the only, let's say, bad lines are related to the peaks that we can see in the picture. In the end, we also characterize the system for other kind of signal, like, for example, this slowly varying one with a ramp of 1 picometer per hour. And we can see that our algorithm is able to correct the bit knot with the megahertz accuracy. And to sum up, so we designed and experimentally demonstrated a silicon nitride stabilizer to lock different laser sources on a 50 gigahertz space grid. For this, we use a locking resonator to lock the multiple laser on different resonances. Then we made a DDO FDM transmission, and we demonstrated that the SNR performance of the edge subcarriers can be improved when the algorithm is working. And for the future, we expect to increase the number of lasers that we want to put at the input. And with the current implementation, we can cover up to 800 gigahertz of bandwidth. So thank you for the attention. If you have questions.
Thank you. Nice talk. Any questions, please?
Yeah, hello. Could you expand a little more on how you differentiate between the different laser source to apply your algorithm?
Okay, I don't have a slide for this, but basically what we do is to act on each modulator separately. No, at the same time, but what we want to do is to encode each modulator with an orthogonal sequence so that we're able to decode at the end, at the microprocessor side, our laser. So we apply CDMA sequence of 15 bits, and that we acquire in 30 milliseconds. And that, I mean, everything we do is at the microprocessor side.
I'll just ask one more question. Yeah. So you've got an encoding to differentiate the two channels. Yeah? So you've got some microprocessor that identifies which laser it is that needs to be tuned to put it back on you. So is that what caused the delay in your results diagram of the 50 microseconds?
Yeah, it depends. I mean, the processing time now is of 200 milliseconds, but it's something that can be improved. For example, increasing the cost of the electronics, for example, or using active modulators, so that we can we don't have to wait for the modulators that are thermal ones to process the information.
Mm-hmm. Okay, thank you.
Thank you.
Okay, we're out of time. Let's move on to the next speaker. If everyone could thank the current speaker, thank you. Okay, the next talk will be a record energy efficient QSFP ELS for co-packaged optics, and the talk will be given by Kyoko Nagai from Furukawa.
Good morning, everyone. My name is Kyoko Nagai from Furukawa Electric. The title of my presentation is Record Energy Efficient QSFP-ELS for Co-Packaged Optics. This is the outline of my talk. Why we need co-packaged optics and external laser source. ELS characteristics reported so far. New structure and characteristics of HRL CWDM TOSA. Thermal design and driving circuitries for ELS. Power consumption and power conversion efficiency for ELS. Finally, the conclusion. First of all, I'd like to talk about power consumption trend of network switch for data center interconnects. This graph shows the relationship between switch ASIC bandwidth and power consumption of switching devices. From 2022 to 2020, switch ASIC bandwidth has expanded from 640 gigabaud to 51.2 terabit per sec. And the total power consumption of switching devices has increased 22 times, while the optics power has rapidly increased 26 times. Hence, suppression of the optics power increase is required. To expand the bandwidth at data centers and power saving, it has been expected to adopt co-packaged optics as a new server architecture. This photo shows the internal structure of the new network switch with CPO. High-density silicon photonics transceivers are mounted together with a switch ASIC at the same substrate. A wide bandwidth switch ASIC generates the heat. However, if a laser source is integrated to a silicon photonics transceiver, it will be operated in a high-temperature environment. Then it becomes worth the characteristics and reliability of laser. Hence, ELS that can driven at the front panel is proposed for the CPO. ELS must have multiple channels, high optical output, and low power consumption. In order to realize lower power consumption, it is preferable to adopt an uncooled laser structure without some electric cooler. Therefore, it's important for LD to achieve a high PCE in uncooled LD condition. I'd like to introduce the characteristics of ELS that have been reported so far. Broadcom reported an 8-channel CWDM ELS using a double height QSFP-DD housing at OFC 2022. First, the characteristics of 8-channel CWDM TOSA. The optical power was 100 milliwatt, uncooled LD structure. Uncooled structure was adopted because it's more efficient. Case temperature was 50 degrees Celsius. Power consumption was 6.2 watt and PCE was 12.9%. Next, I'd like to introduce the ELS that equipped with the TOSA mentioned earlier. According to LI curves, to obtain a fiber optical output power of 100 milliwatt with LD bias current 450 milliampere at a case temperature of 50 degrees Celsius. This graph shows if the case temperature exceeds 50 degrees Celsius, the optical power could not achieve 100 milliwatt. Maximum case temperature was reported at 50 degrees Celsius to obtain the optical power of 100 milliwatt. Power consumption was 7.7 watt and PCE was 10% at the case temperature of 50 degrees Celsius. Here is the TOSA we reported so far. To obtain an optical power of 100 milliwatt, the LD bias current was 350 milliampere. Case temperature was 55 degrees Celsius. Power consumption was 4 watt. Power conversion efficiency was 20%. We also reported an 8-channel CWDM ELS with the standard QSFP housing. The ELS also achieved the optical power of 100 milliwatt at a housing temperature of 55 degrees Celsius. In order to achieve a high PCE, we worked on updating TOSA and reducing the power consumption of the driving circuitries for ELS. We report about our energy-efficient ELS. To save the link power in data center interconnects, it is highly demanded to realize a higher PCE for an ELS. This figure shows a schematic top view for the TOSA structure. Each LD and optical components are mounted on substrate with 1.2 mm pitch. The laser beam is coupled to the PMF by focusing lens through an optical isolator. For this 8-channel CWDM TOSA, SOA integrated DFB LD is employed to obtain high optical power. In order to realize high coupling efficiency of laser to PMF and to obtain high PER, each optical component and PMF cables are precisely aligned and fixed. The coupling efficiency was improved from 70% to 85% by updating the optical coupling system. And the new substrate was adapted for higher thermal conductivity. These updates have resulted in lower LD temperature, and LD bias current also could be decreased. This graph shows the simulated LD temperature at a TOSA case temperature of 55 degrees Celsius, and in a channel simultaneous drive of LD current is varied from 0 milliampere to 500 milliampere. In the previous structure, the LD current is 400 milliampere to obtain the fiber-coupled optical power of 100 milliwatt. With the new structure, the fiber-coupled optical power of 100 milliwatt is achieved with the LD bias current of 300 milliampere. In the previous structure, the LD temperature increased to 9 degrees Celsius from the case temperature, while in the new structure, the temperature rises as small as 5 degrees Celsius. By updating the optical coupling system and improving the heat dissipation structure of TOSA, the LD temperature was able to be lowered by 4 degrees Celsius compared to the previous structure. A lower LD temperature contributes making a PCE of the LD higher. This graph shows IL curves at the TOSA case temperature of 25 and 55 degrees Celsius. An LD bias current to obtain a fiber-coupled optical power of 100 milliwatt is 270 milliampere and 300 milliampere at an operating case temperature of 25 and 55 degrees Celsius, respectively. The power consumption of TOSA is 3.4 watt and 3.7 watt at an operating case temperature of 25 and 55 degrees Celsius. The total power consumption is 3.7 watt and power conversion efficiency is 21.6% at a case temperature of 55 degrees Celsius, even with the optical coupling loss. At the front panel of the network switch, the QSFP ELS is inserted to a cage which has an air cooling heatsink at the top. Therefore, the top surface of housing is thermally connected to the air cooling heatsink. The bottom surface of the TOSA substrate is thermally connected to the top housing. In order to suppress the difference between the TOSA and the housing temperature of the QSFP ELS, in the thermal simulation, the temperature at the top housing was set to 55 degrees Celsius. Bias current of LD was 300 milliampere. From the simulated temperature distribution, the temperature difference between the TOSA and the top housing is calculated as low as 0.7 degrees Celsius. The QSFP ELS can maintain a very similar characteristics with the TOSA. Here is the inside structure of QSFP ELS. A-channel TOSA and PCBA are built in a QSFP housing. Functions of PCBA are auto power control or auto current control mode. Status monitors monitor the driving status through I2C bus interface. The electrical card edge mating interface of PCBA is compliant with the standard QSFP28 optical transceiver, except for high-speed interfaces. The PCBA also has LED driver circuitries, as well as a power supply regulator and a temperature sensor microcontroller unit. Each LD accompanied with an LED driver. The LED driver circuitries employ DC-DC converters. To save the power consumption, the DC-DC converters reduce the supply voltage of 3.3 volt to the maximum LED driving voltage, which enables supplying an LD current of 500 mA sufficiently. This graph shows the power consumption of QSFP ELS. Dotted line shows calculated value, and open circle dots show measured values. The measured values has a good agreement of the calculated value. As a result, the fiber-coupled optical power over 100 milliwatt per channel with an LD bias current of 300 milliampere at a housing temperature of 55 degrees Celsius. The ELS can be driven with a total power consumption of 5.6 watt and power conversion efficiency is high as 14.3%. This graph shows measured relative intensity noise of ELS, which integrates TOSA and PCBA. relative intensity noise was measured the frequency ranging from 10 MHz to 30 GHz at a fiber coupled optical power of 100 milliwatt at room temperature. It is less minus 150 dB per Hertz. This is my summary. We updated the TOSA structure. Optical coupling efficiency is increased to 85%. Laser temperature increase is suppressed as small as 5 degrees Celsius. Power consumption of TOSA is as small as 3.7 watt with a fiber coupled optical power of 100 milliwatt at a case temperature of 55 degrees Celsius. The TOSA achieves a PCE as high as 21.6%. The high energy efficient driving circuitry is designed and fabricated. By updating the TOSA structure, designed and fabricated of the driving circuitries, the power consumption of ELS as small as 5.6 watt and PCE is 14.3% with a fiber coupled optical power of 100 milliwatt at a case temperature of 55 degrees Celsius. This is all for my presentation. Thank you very much for your kind attention.
We should really move on. I'm sorry we don't have time for questions. Thank you very much. Okay, let's move on to our next talk. The title is Integrated Programmable Mode Generator and Multiplexer on a Silicon Chip. Is the speaker here? Yes, okay. The speaker is Vishal Badandri from the University of Laval, Quebec, Canada.
Good morning, everyone. I am Vishal Bandari, and I'm going to present our work on integrated programmable mode generator and multiplexer on a silicon chip. I'd like to acknowledge my co-authors Yushan Shen, Simon Lavasa, Professor Rush, and Professor Weishi. We come from COPL at the University of Laval in Quebec, Canada. So this is the outline of my talk. I'll be talking about the motivation and some of the previous works that we have accomplished. I'll be describing the design that we propose and briefly explain the working principle. After that, I'll explain some experimental results that we have achieved so far and conclude the presentation. So what's the main reason behind this research? Why do we need a mode multiplexer circuit or arbitrary mode generator? So there are several approaches with the increase in data transmission speed requirement for multiplexing, such as WDM, the wavelength division multiplexing, and spatial division multiplexing, the SDM. So we are more into the SDM schemes. We have already done a lot of work in LP modes and OM mode generations. So there are several advantages and disadvantages of each of these modes. So I don't want to go into details of each one, but what we think is being able to generate each of this mode from a same chip will always be advantageous for different applications. So in this work, we are attempting to generate a different mode generation from a single silicon photonic chip. So previously, there are some work that generate OM modes from silicon photonics chip. In the first work, here they use grating antennas positioned in a spherical shape, like in a circular shape, and by playing with the phase of it, they can generate different orders of OM modes. In another work, they again use different kind of gratings. By positioning it in such a way and playing with the phase, they can again generate. But in this case, since the emitters are limited, they could only generate up to 5 OM modes. In our previous work that we have published in JLT this year, so we could present the record numbers of 46 OM modes, 23 on each left circular polarized and right circular polarized modes. So the good thing about this design is we use optical phase arrays with 2D gratings that could generate a circularly polarized beam instead of linearly polarized beam. In order to get a different kind of modes out of a circuit, we need some kind of programming, or we need some kind of switching mechanism. And recently, the programmable circuits are taking more attraction from a lot of people. There are recent works that exhibit different kind of programming. So in this kind of mesh circuits, they use MGI, the mass gender modulator interferometers, to switch different signals. So inspired by this, we also design our own mesh to switch different signals. So by combining our ideas with the switches, so we come up with a new design. This is our switching circuit. We call it as a linear operation circuit, and we cascade it to our OM generation circuit, which can give us the outcome. So by playing with different combinations of bias currents in the linear operation circuits, the switch can be done to generate different OM modes, CV modes, and LP modes, all from the same circuit. Conventionally, in order to generate LP mode from a chip, there are some works who use a combination of gratings in such a fashion that they could generate different modes. But these are mostly linear circuits, and they just do some linear multiplication of different vectors and get the results. But in order to get everything from the same chip that we can generate OM, so we found that there is another way of generating the LP modes using OM modes. So as you can see in the equation, we can generate LP mode by combining 4 different OM modes of different charges and different polarizations, but all of them are in the same order. So this is the OM generation circuit that we already published. So you can refer to some of the papers that we have for more details on the working of this one, but I'll just briefly explain about this. So we have multiple input channels. Each of these channels are mapped to a specific order of OM mode. So by sending light from that specific channel, we can generate different OM modes. We have the star coupler to distribute the light to all the emitters and also allow the phase and amplitude distribution. We have phase shifters and variable optical attenuators on chip so that we can correct the errors that were induced by the fabrication. We have MMIs that acts as a on-chip quarter wave plate so that we can generate circular polarized beam instead of linear polarized beam from the emitters that we have. So the top portion of this chip acts as the left circular polarized section, and the lower part is the right circular polarized section. So by inputting the lights on this section, we can generate LCP modes, and by inputting the light from these channels, we can generate the RCP modes. So in order to combine these modes and use it at different functionality, we have the LOC circuit. So this LOC circuit consists of crossings, waveguide crossings, and we also have some Mach-Zehnder interferometer switches. So that act us to help us redirect the light into different inputs, and it consists of a phase shifter that will allow us the switching of the channels. So based on the combination of the MGI switches, we can redirect the light into either the LCP circuit or to the RCP circuit, or we can even split to both of these circuits. So in order to generate the LP mode, as I previously explained, we need 4 different OM modes. To do that, we use the MGI as a 50-50 splitter so that we can split light and send it to the specific order of the mode. So by this, we can generate LP modes. In order to generate cylindrical vector mode, we need to excite 2 AM modes of the same order but different polarization and different charge. So to do that, we excite first MGI as a splitter but another as a switch. So by doing this, we can either select these 2 specific modes or specific these 2 modes in order to generate cylindrical vector modes. And similarly, we are able to create the OM modes specifically. So to do that, we just use MGI as a switch. So by doing this, we can trigger different OM modes specifically. So this is the design of our circuit. It's a pretty big circuit. It's almost 8 millimeter by 8 millimeter in size. So this is the fabricated circuit. We have placed the linear operation circuit at the center, the RCPs and all the VOAs and phase modulators for LCPs here, for the RCPs here, and we have the emitter over here. So in order to make this work together, so we need to make sure that all the emitters are emitting at the uniform intensity. So to do that, we use the chip as a multiplexer, so we try to emit a specific order of OM beam. So as you can see in this first image, the beam are not well, and all the intensities might be slightly different. So we try to correct the intensity using the VOAs. And again, since it is also a demultiplexer chip, so we can input a specific order of OM mode into the chip and track it to the specific input that can generate it. So considering the light coming to the specific target input as the reference, we measured all the outputs from rest of the inputs as the crosstalk. So as you can see, in one of the situation, we had more power and one of the inputs than what we expect at the targeted one. This means that was not well phase optimized. So by playing with the intensity and phase modulus together, we could reduce it to less than 13 dB crosstalk. That means we have more light on the specific mode itself. So as you can see, there is a little difference between the LCP and RCP tuning because it's a very time-consuming process. So also there are some fabrication errors that happens in this big circuit. So we are trying to optimize this in our future generations. So once all the calibration of the circuit is done, once we set all the phase and intensity tuners, we use the LOC circuit to generate the LP mode, and we got some interesting results out of it. So when we see them in side by side to the theoretical expected outcomes, we can see that we could successfully generate different orders of LP modes. We can see that the intensity is not that uniform, but we assume that because the crosstalk in two different RCP and LCP circuits is slightly different, so we assume that the interference is not happening properly. So we are working on it, and also we are also working on how to numerically characterize this in terms of purity of the polarization. So in overall, we just demonstrated a circuit that could generate OM modes, LP modes, and also it is able of doing CV mode, which I didn't show it right now. We can have a good crosstalk values, and we think that this circuit can be used for a portable mode generator in future. I'd like to thank the funders for this project, and I also like to thank Nathalie Bacon and CMC Microsystem for the technical support. Thank you very much.
It's very interesting. Thank you. Any questions? And maybe I could ask a quick question about your waveguide crossovers.
Sorry?
Your waveguide crossovers.
Oh, sure.
Yeah, they're not shown at 90 degrees. Were they at 90 degrees? And if they weren't, what was the crosstalk of each crossover?
Okay, for this, this exactly are like we have placed it at 90 degrees. Although it looks like this,
Yeah.
It's just a schematic, but the layout is 90 degrees.
Okay.
And right now we are having a crosstalk of around minus 37 dB across the branches.
Okay, thank you. We've got time for more questions if anyone would like to ask anything. No? If not, let's thank the speaker. Thank you very much. Okay, we're a bit early for the next one, but the next paper is our final paper in the session, setting up multiple free space orthogonal communication channels automatically between photonic chips. And the talk will be given by Syed Mohammed Sayedin Nevada from Politecnico di Milano.
Okay, thank you for the introduction. My name is Syed Mohammed Sayedin Nevada. I'm a PhD candidate in Politecnico di Milano. And this is a work in collaboration with the University of Glasgow, Sant'Anna, Pisa, and Stanford University. So what we want to do here is actually performing a mode division multiplexing, but unlike the previous talk, we want to use an arbitrary beams through this free space path and performing and be reconfigurable at the transmitter and the receiver side. So I'm going to introduce the device concept, and then the mesh circuit and optical setup, and at the end, the experimental results. So we want to manipulate free space optical beams on the chip. In conventional optics, we can do free space communications, long range, short range. We can have LiDAR for range and velocity measurements. We can manipulate the beam as we want. Our background is in photonics, so we fabricate, design the waveguides, passives, sources, modulators, detectors in order to have a certain functionality on the chip. And advantages of integration is obvious for this audience in terms of reliability, cost, footprint, etc., etc. So what we are aiming here is to perform, is to have a free space communication link and perform mode division multiplexing. So we use photonic chips at the transmitter and receiver side in order to communicate with each other through this free space path. And in addition to that, we want to find the optimal mode set that can propagate through this media. So we enter with single modes. We become multiple mode. We multiplex them through this channel. And then once passing through this channel, at the receiver side, we demultiplex them and go back to the single modes. A device like this, you can imagine that should consist of different parts. We need a photonic processor core in order to process the light on the chip. We need an aperture on the chip in order to couple the free space beam into the chip and out of the chip. And we need or may not need waveguide fiber ports in order to go to the conventional fiber optics communications equipment. So this is the device concept as a reconfigurable model multiplexer demultiplexer. I'll go through different parts of this device, starting with the photonic processor. So what we propose here as a photonic processor, we use the mesh waveguides of Mach-Zehnder interferometers. So how do they work? If you consider this bottom Mach-Zehnder here, it is actually a tunable beam splitter. So you enter with your two inputs. You apply 2 degrees of freedom, 2 phase shifters in order to change the relative phase shift and relative amplitude between them in order to couple, for example, all the power of this input to the upper output. How we can do this? We can read the photodetector at the branch, output branch that we want to null. We close the loop and we act on phase shifters in order to couple, to sum up coherently the 2 inputs at the output. If we have more than 2 inputs, you can imagine that we can cascade these Mach-Zehnders like this in diagonal fashion. By applying proper phase shift on each Mach-Zehnder, we can couple all the light to the output waveguide as here. This is one of the features of this device, which can self-align to an arbitrary input beam. Another feature of this device is that when we have an orthogonal input to this device, which is stated here, so the inner product is 0. None of the power of this second beam appears at the first output waveguide. So it passes entirely through the first Mach-Zehnder row, and you can imagine if we implemented another row of Mach-Zehnders, we can apply proper phase shift on them, and then couple all the light of the second input to the second output. This is a well-known approach in the literature, so we are implementing a unitary matrix implementation using these mesh waveguides of Mach-Zehnder interferometers. So you input with your orthogonal beams and you change the representation so that you map your modes to the output waveguides here. As for the aperture, we use grating couplers here. So we configure them in an array like this here. And these are vertically emitting grating couplers, single polarization. We performed this experiment last year, which is published here. We prepared 2 Hermite Gaussian beams. We shown on the aperture of this chip here. And by configuring the Mach-Zehnder rows, we can couple all the power of these inputs to different output waveguides. So in this way, we separated the overlapping orthogonal beams. We performed the demultiplexing or descrambling of these 2 inputs. If we have a free space path, we can imagine that we may have cross-coupling between the input modes, the input beams that we shine to the chip. So our proposal is to use another chip on the transmitter side in order to be adaptive also on the transmitter side. So we both generate and separate these orthogonal free space beams that can pass through this free space path. In this way, we can establish multiple orthogonal commission channels automatically through an arbitrary scatterer. Here we are using finite number of apertures, grating couplers. So at the end of the day, we have finite number of modes that this system can handle. This is a well-known approach in the literature in telecommunications. So what we are doing here is actually we are implementing in situ the singular value decomposition of the transmission matrix. So you have your transmission matrix, which can be decomposed in the singular values and singular vectors, U and V. And by configuring these Mach-Zehnders, we are actually estimating the U and V matrices, so the singular values of the system. So once we propagate through this system, at the end of the system, we have these singular values. Here, for example, we implemented 2 rows of Mach-Zehnders. So at the end of the day, we have a singular value matrix 2 by 2. The on-diagonal terms defines the end-to-end power coupling, and the off-diagonal terms crosstalk between these established channels. So we designed and fabricated this circuit, silicon photonics, platform, 220 nanometer waveguide, and AMF foundry MPW. As I stated, we implemented 2 rows of Mach-Zehnder, 8 Mach-Zehnder in the first row, 7 in the second row, and we implemented thermo-optic phase shifters, titanium norton on top of these Mach-Zehnder interferometers, as you can see in this figure. So at the end of the day, we have 9 by 2 mesh of Mach-Zehnders. We implemented 3 by 3 square RF vertically emitting grating couplers. The distance between them was 50 micron. The working wavelength is 1.55 micron. And as you can see here, these are our optical antennas, the aperture of the chip. So as for the optical setup, we simply use 2 Fourier transform lenses. So the first lens is collimating the beam that is coming out of the transmitter. We use a mirror to steer the beam to the horizontal direction. It passes through a scatterer, which I defined next. And then at the receiver side, we capture the beam and focus it to the aperture of the second photonic chip. Here you can see the photograph of the setup in the lab, consisting of different parts: the photonic chip parts, the bulk optics for collimation focusing, and the SLM that I defined next, IR camera for capturing the beams, and control electronics. For control electronics, we used custom designed electronic boards. As you can see here, different acquisition and actuation chains based on FPGA. And we use the dithering control technique for bringing this Mach-Zehnder in the right bias point. So how we can tune this system? There are different ways to do it. Actually, one way is to send a light forward and backward through this system. So you start with your transmitter with an arbitrary configuration of the Mach-Zehnders. You pass through your free space path, and then at the receiver side, you're configuring the Mach-Zehnders. Once it's finished, you can reverse the light direction. So this is going to be the transmitter with the Mach-Zehnders configured previously. So now your receiver at the left side, we configure them to couple all the light that passes through these Mach-Zehnders. Going through this loop, backwards and forwards, we're converging to the solution of this system. Here you can see a simulation of this procedure. So we started with an arbitrary phase shift on the Mach-Zehnders on the left and right. As you can see, these are the first 3 modes of the system out of 9 modes. You can see by going through this procedure, in this case 4 iterations, we can converge to the solution of the system, which is in this case resembling the Hermite-Gaussian modes. Here I'm showing you the singular values associated to the singular vectors. As you can see, the power allocation, so the singular values of the system is not equal, so the channel is non-unitary. And you can see that the second and third modes are degenerate actually. As you can see that they share similar shapes also, yet with a 90-degree rotation. Note that here we are showing only a portion of the beam because of the long distance, big distance between the array elements. We see multiple diffraction orders in the far field pattern, and we are only showing a portion of the beam, so one of the replicas. So for experimental results, we run these configuration processors forward and backward, and we establish these two orthogonal combination channels automatically. As we expected, the second and third modes share similar shapes that you can see here. The measurements have good arguments with the simulations, and they are degenerate. So the combination of these solutions may be accepted as you can see here. So in this graph, I'm showing you the coupling between these two modes and the crosstalk. So this second mode or third mode is coupled with lower power, 3 dB, as we expected from the simulations in previous slide. However, if we tune the transmitter and receiver side, we can see that the crosstalk between them is below -30 dB. Here I'm showing you a video of the tuning procedure. So we reset the Mach Zehnders in different in arbitrary phase shifts, and once we tune the system, we can converge to the solution of the system, which is in this case these donut-like shapes. As a further demonstration, we wanted to emulate the perturbation of the free space link. So we inserted metallic masks designed with the same repetition of the far field with different shapes. Here we are showing only one of the shapes, which is donut-like, for obscuring the beam. So we put this mask in between for obscuring the beam that is passing through this free space path. Another demonstration is using with an SLM. So we introduce phase front perturbations for the beam that is passing through this free space path. In both of the cases, you can see that without tuning the system, so you insert your mask here, without tuning the systems with these O marks, you can see that you are degrading the power of the coupled modes, and also the crosstalk between them is degraded. However, once you tune the system, you can see that, for example, in this case or in this case, you can see that we are compensating partly for the channel loss, and more importantly, the coupling between these two modes are retained to below 30 dBs. So in conclusion, this system performs an in situ implementation of singular value decomposition. This allows us to have multiple orthogonal channels to be formed simultaneously. Thus, we are performing multiplexing and demultiplexing. We are doing it automatically and without any calculations of the transmission matrix, and only using a simple power minimization of the Mach Zehnder rows. This system can self-configure to adapt to the perturbations introduced in the free space path. And this can be applied to the modulated signal, as we are demonstrating here. We use a 5 gigabit per second OOK in NR0. So without the scatterer, this is a reference. We put the scatterer without tuning, we get these eye diagrams. Once we tune the system, we get these eyes open again. And with this, thank you for your attention. I want to have your questions.
Thank you, very nice work. Any questions? Okay, I'll ask a question. So your chip can demux multiple orthogonal modes simultaneously. Could you just go over how it's done? Is it the unitary matrix part of it? Yeah.
So here. Yes, this triangular matrix implementation, the Mach Zehnder mesh implementation, is famous for implementing a unitary implementation of the matrix. So if you have your inputs orthogonal, you can map them. Actually, you are changing the representation by this unitary matrix, and you are mapping your modes directly on the physical waveguides here. And that's the way that it does this.
Okay, thank you very much. Any other questions? No? Well, if not, that's the end of our session. Please thank the speaker. Thank you very much.